So we're going to talk about regenerative energies. Recently worked on an application with an antenna, and this was a rather large antenna. You can see the little person here and the big antenna there. In this application, we were using a 2-axis Xenus for azimuth and elevation. The one Xenus has a small regen resistor with a fan that can dissipate energy. So an awful lot of energy. The problem in this application was when they powered up, the motor power wires were not connected. The antenna started to move. Then you got a following error fault, and then the brake turned on, but the momentum had increased to the point at which you can't turn your brake on when it's spinning 6,000 RPM. You tend to burn up your brakes that way, so the motor brakes aren't designed to be turned on and running constantly at 6,000 RPM. That could damage the brake. I mean, you could turn it on, but all the particulates start gathering up inside your brake, and it's just not a normal mode of operation. The best way is to come to a controlled stop and then hold position and then turn your brake on. Although we do have a new feature, it's a safe brake release, and it monitors the UVW before you enable to make sure you actually have your motor power connected. So we're going to take a look at a large motor. We've got here with a Xenus. So this is the big motor and the little Xenus. 120 or 240, 20 amps continuous, 40 peak. So that's 6 kilowatts of power. And then you've got this idea that someone's going to put a little ohmite resistor in there that's like 50 watts to handle all the energy. Maybe, after peak, like the resistor manufacturers tend to say what the rated watts is, but they don't specify the peak. The important thing is not to overheat and burn up the resistor. It would be like a very large resistance when it burns up. So you can measure it. Maybe this is like a little 60 ohm resistor used in the 2-axis Xenus or inside of a Xenus compact. But this is a real regen resistor, the Copley regen resistor, coils inside of aluminum case. I mean, this thing can get up to 200 degrees C, fry some bacon on it. We set some safety limits in the drive for default, but we can increase those. Just remember, this gets really hot. There's some mica in here to keep the coils separated, so high shock and vibration. This isn't just a standard resistor from the company. It's a Copley regen resistor. I've got it wired up to the Xenus. There is a short circuit protection, so if you short the wires, you'll get a short circuit. So I don't know, you could use a fuse if you want, but that doesn't make any sense. Another item to go open or cause a fault. I just wire it directly. We've got an IGBT in here that can dissipate all the energy we can put out. It can't dissipate all the energy that you put out over a long period of time and then take back, like gravity and whatnot. So let's take a look at the energy in a system and figure out how to size a regen resistor based on the energy in the system. I like to use this big ball at a certain height as an example of stored energy. So we try to consider all the energy that can be stored in a mass. It can be due to gravity. It could be moving at a velocity, or it could be rotating like an inertia. This is just a way to model the energies. Now, there's other energies that go into the system, like wind and pushing, external pushing. Maybe another motor is driving the system, and the energy goes for like a dynamometer. But so the energy that goes into the system is like the energy returned when you're trying to stop. And when you hold position, I guess if the motor is spinning, you can get energy. If the motor's not spinning, there's current, but there's no voltage. In order to get work done, you can push all you want against a mass. If it's not moving, you don't get any work done. Okay, so voltage and current or joules over time. The watts, right, measures not just the current or not just the voltage. If you're coasting, you're not, regenerating. You're just generating a voltage. If you apply a load to it, then you get current, and so work is done. Anyway, so this energy that's stored in the system could be 1/2 the mass times the velocity squared if it's moving, or 1/2 the inertia times the angular velocity if it's rotating. The motor shaft plus the load, that sort of thing. And then if it's like an elevator, you have the mass at a certain height due to gravity, presumably on Earth. But hey, maybe you go to the moon, or maybe you're in outer space where there's no gravity. This is a model of the system. So the energy that goes in leaks out of the system everywhere. Okay, so the load bearing has some friction. Gears have friction. Apparently, they're not all 95% efficient. They're like 75% efficient. Depends on what goes on in your gear. So energy squirts out of the gear by heating up. Your motor has a winding resistance. So the current squared times the resistance of the motor winding. Energy dissipates in the motor. The drive is in the system. It's got some on resistance of a FET. So I'm going to use 0.4 ohms. Some drives are less than that. A lot of motors are low resistance now, so maybe it's direct drive and no energy is dissipated anywhere, but some is. You've got viscosity and some friction, unless it's air bearing. But so we can model the drive at let's say it's 10 amps squared, 100 times 0.4. That's some watts. There's a capacitor in the drive. There's usually a local bus capacitor which can charge up. Maybe it's 1,000 microfarads, so 1/2 CV squared. And so the energy stored on the capacitor is 1/2 CV squared. The energy lost in the drive is I squared times the on resistance of the FETs. And this is just, could be less than 0.4 ohms, but I'm just throwing that out there as like, hey, I'm dissipating at 10 amps, I'm dissipating 20 to 40 watts in a drive. And the winding resistance, got 10 ohms and 10 amps. Wow, that's a lot of watts. I squared 100 times 10, that's 1,000 watts in the motor winding. So sometimes the energy doesn't all get back to the cap, it leaks out in the system everywhere. So that's a good model. If you do have the blocking diode to prevent energy to go back to your power supply, then this cap will charge up and energy doesn't get back to the power supply, or burn up your power supply in some cases of a regulated supply like a crowbar circuit. But you need some bleeding or regen resistor added across this, so you turn off and on the regen resistor to dissipate the energy. So we'll take a look at this making a move here. We can accelerate and decelerate slowly. So a lot of energy goes into the system for acceleration. I'm doing 20 amps for XL, and then decel is like 5 amps, and then less as friction takes over. But you can see the voltage is pumping up, and I'm hitting about 300 volts. If I increase my deceleration rate without the regen resistor connected, it looks like it stopped, but there was a little fault there as I got to the over voltage. So I hit 400 volts, I shut down, the motor coasted, and then it turned back on sometime later. We need to turn on the regen resistor. So in CME, we have the ability to configure this. I've got the 15 ohm, as I have the larger current drive, the 15 ohm view settings. I'm going to say OK. If I made it a custom resistor, I could see the values. Oops. Let's make this say OK. And yeah, okay, so I'm going to view it. So it's a 15 ohm, 60 watt, 10,000 watt peak. I mean, we're talking a lot of, at least 5 times the rated current for a short period of time, maybe about a second. We set it to 65 watts. I mean, this can do 400 watts. That's a big resistor. It's just going to get stinking hot. So check the thermals on it. If you did reconfigure this, you could increase the watts. Like you could put in 200 watts or 400 watts, depending on how hot you let the thing get. We'll take a look at the graph on that in a moment. Or you could get your own resistor and configure it properly, but just make sure that you have the right resistance in here and the right rated watts. I've used to increase it to 800 watts for lots of energy kicking back, like from a big antenna. I've used 2 in series with 2 in parallel, so 4 regen resistors still equaling 15 ohms, you know, so that's possible. So we'll take a look at the documents for this. So under support, under Xenus, we've got the manuals, and there's a regen guide. The regen guide shows the Xenus and the resistor. And you can look at the temperature. So when you're doing a 200 watts, it's hitting 150 degrees, and the graph sort of ends at 250, extrapolating. Yeah, so probably about here would be 200 degrees Celsius, and maybe that's 300 watts. So yeah, there's a point at which you overheat, so watch the temperature on the regen. The other nice thing about the guide here is that it does have a whole section on calculating regen resistor sizes based on energies stored in the inertia or the force of a linear, and how to store on a capacitor. But it doesn't model like the real world and everything. There's another note here which is useful for the Accelnet. The Accelnet can fire an output to turn off and on an external regen resistor. And so this is like built into the drive is the settings, but you have to provide the resistor and a solid state relay and a flyback diode and a reverse diode and local capacitance. So you just turn off and on the solenoid connected to the output of the drive to a smaller or necessary regen resistor, and of course we'll help you calculate that. And CME, there's some configurations of an output. You can put the turn on, turn off voltage, the resistance, and the peak and continuous watts and the time. And so we'll take a look at what happens when you turn on the regen resistor and the energy starts to dump to the regen. You can see it turned on here. Increase the deceleration. You can see it turning off and on more effectively. And you can repeat this duty cycle. The default setting is 65 watts, but you can see as it hits the voltage, it turns on. As the voltage droops down, it turns off. So off and on, and then not used. So you can measure the cycle of the regen resistor and determine and you can measure the current, actual current, and voltage terminal servo to see the energy that's coming back. So I'm hitting probably terminal voltage servo in blue, looks like about, yeah, some pretty high voltages and some, yeah, like 100, there's 100 volt down here. So you can see the voltage dissipate and you can see the current, again, 20 amps for decel. So that's the basics there. And again, you could configure an output. The Xenus Compact has an internal regen resistor, and there's a fan that turns off and on, but it's only 20 watts continuous, although it can handle all the peak that comes back. There is a space for an external regen resistor. If you buy 1,000 drives, I'm sure we can do something like, you know, new Lexam with a hole punched here. But that would have to be for a very special case, because then we have to go back to UL and CE testing for this. So there's a possibility. But buy the Xenus XTL, the Xenus Plus, or the Xenus Standard. Both have the big regen resistor capability. And if I still have time, we can see how to configure the output. So digital output, program control. Well, I'll just take it over and use it for regen. I'm not seeing it in the list here, so it must be for the Accelnet. Anyways, Yeah, we can roll our own low cost poor man's regen. Just pick the right resistor. We can help you.